Hello everyone. In this video, we are going to talk about aliasing in digital signals. If you noticed on my channel, I have created a new playlist called Digital Signal Processing. It's a playlist that I wanted to start long ago and I decided to start it. So there are two new playlists. One of them is Linux, the other one is DSP, and my goal is to add videos to them. And then I'm gonna go to ROS. So right now, the only thing I have is the video I published earlier, which I put it under playlist MATLAB, but it also really more belongs to the digital signals. And this is about the frequency content of a discrete signal to visualize it in Simulink using FFT block and FFT shift. So now we're going to talk a little bit about aliasing. And I know I have to make another video and talk a little bit about the FFT itself. So what is the fast Fourier transform does? First Fourier transform and then probably fast Fourier transform. So let's just start about aliasing, a common phenomena when you are trying to sample an analog signal and go to digital. Now, some of the pictures here are coming from this very great book, which is one of the most important textbooks in DSP, and that is called Discrete Time Signal Processing by Oppenheim. That is one of the best books out there, and I have a couple of pictures from this website. So what do we have here? So you know that when we want to go from an analog signal to a digital or discrete signal, basically a discrete time signal, we are going to sample the signal at specific intervals, right? Every t seconds. This t is called the sample time. It could be a very small number or a little bit bigger. It's under our control typically. So here I can say that I can, if my continuous signal is x sub c of t, I'm gonna convolve it with a train of impulses. These impulses happen at the times nt, their magnitudes are all 1, and there are an infinite number of them from basically negative infinity to positive infinity, and this n is an integer number. So basically, if you consider your time axis, right? So you have one here at 0, you have one at t, you have another one at 2t, and negative t, and so on and so forth, okay? So these are what, at this integer multiples of t, this is a train of impulses. Their magnitudes are all 1, and we convolve it with the signal to basically get the value of the signal at those time points, right? So here, look, this is the continuous signal, is this dashed line here, right? This curve. And now I'm going to sample it at a sample of t1. So at 0, t1, 2t1, negative t1, negative 2t1, and so on, I'm going to get the value of the signal, which are going to be all of these points. And so my discrete time signal is going to be lines that are as tall as those values at those points. There we go. So here you are going to get this one, right? So this is the discrete version of these points, is the discrete version of the continuous signal, which you can call it x sub n, which are all of those x and t's at all integer numbers of n. Now, of course, if you change the sample time, what's going to happen? So here we're going to use 2 times t1. So we use a bigger sample time. Therefore, we're going to get fewer samples, right? So now at 0, basically t, which is 2t1, at 2t, which is 4t1, and similarly at negative 2t1 and negative 4t1, we are going to sample it. So basically every other one. So once we get something here, then we jump to this one, and similarly like that. So you're only going to get these points, and if you discretize it, there we go. Basically what you get is here, this one is this one is here, this one is here, and this one is here. And here are more samples. You spread it more in time, And now if you look at it, you see that the shape of him, if you connect them together, right? If you connect these points together with some kind of curve, you see that the shape is a little bit different, right? So look at this one and look at this one. You see, they are not exactly the same. Because here you got a lot more data than you got here. So the sampling does affect the shape of this xn, right? Ideally, if we can sample it at every, I don't know, very, very small number close to zero, when this t goes to zero, then my discrete time signal is very similar to my continuous signal, but that is not possible. We have to pick some number depending on our hardware, and so the result of that sample time is going to be different looking signals. Good. Now what happens in the frequency domain? This is in the time domain, right? When you sample a signal which is convoluted by a pulse train, basically, what happens in the frequency domain? So let's take a look at the frequency domain. So the inverse of the sample time is what we call the sampling frequency, fs, which is in hertz, and 2 pi over that t is, again, sampling frequency, but in radians per second. Good? So for instance, if our sample time is like 1 millisecond, then the sampling frequency is 1,000 hertz, and then 2 pi over that, this is going to be 2,000 pi radians per second. This is my sampling frequency. Now, what happens again? What happens when you sample a signal? So look here. Let's say this is the continuous signal, but instead of time domain, it's now in the frequency domain. So this cap omega is your frequency. In some control books, you see it's replaced by small omega. That's the same thing, basically. It's just cap omega versus, that's the frequency domain. So this is the frequency content of the signal. This signal has frequencies anywhere from negative omega n to positive omega n, right? And the magnitude at these frequencies are different. Outside this range, the signal has no frequency. So the frequency in this signal is limited between, let's say, negative omega n to positive omega n. And it doesn't need to be symmetric. I mean, it could be completely asymmetric. Here, just for simplicity, we consider it symmetric about omega of 0. So this is the magnitude of x versus omega, right? Now, if you sample the signal, what's going to happen in the frequency domain? When you sample a signal in the frequency domain, this frequency magnitude plot is going to be replicated. So you see this one that you had in the beginning, now you're going to get another replicate of that, another replicate, and so on and so forth. And how far are they away from each other? In other words, if the center of this one is at omega of 0, what's the center of the next one? You see that the center of the next one is at omega equal omega s. The next one is at 2 omega s, then negative omega s, negative 2 omega s, and so on. So you get replicates of the frequency plot at distances of what? At distances of omega s. It will be replicate of the original signal. Good? Fine. So this is the frequency magnitude plot for the discrete time signal as opposed to the continuous one. Very similar, but just repeated in the x direction, in this case the omega direction. Fine. Well, what's the problem here? The problem is this. So this one here that you can see, if you look at it, your sampling frequency is related to this omega n in the signal. This omega n, in some textbooks, we also call it omega max. This is the maximum frequency that you have in a signal. Okay, you don't have anything beyond this. No frequency beyond this exists. Now, if you look here, this distance from here to here is omega n. This one from here to here is omega n. And this distance from here to here is what? Is omega s. So you have 1 omega n here, 1 omega n here, right? And there is also some gap between them to get it equal to omega s. In other words, omega s in this case is bigger than 2 omega n because there is some gap between them. Okay, and you get this plot. Well, no problem. This is my frequency domain, frequency plot of the sample signal. As long as my sampling frequency is bigger than 2 times maximum frequency in the original signal. Now, aliasing is when this relation is not valid. This one becomes violated. Your sampling frequency is less than 2 omega max. Now what happens? You still get this triangle in this case repeated, but now there is no gap and there is instead overlap between them, right? So this time, this is omega n, right? And this is omega n, right? And this is omega s, and you can see that omega s here, which is this one, is less than these 2 omega n's. There is this much of overlap this time. This is the overlap between them. So you get all of those triangles, and then those triangles have to be added together because they are overlapped. So what would you get? If you look at the overlap region, you have this line and you have this line. Okay? Right? So what would you get? Yeah, look at this middle point. Both of them have this value. So your actual value is going to be, whatever this number is going to be 2 times that, which is going to be this level. Yeah? And when you are at this corner of it, what happens? Yes, the signal on the right is 0, but the signal on the left is here. It goes all the way to here. So when you add 0 on that number, again, you get that same level. And continue on the right side, you get the same thing. So over that overlap region, what would you get? You get a constant number. Look, you get this. And now what? Now, let's ask this important question. If I go back and look at the case that sampling frequency was high enough, remember, by sampling, I went from continuous signal to discrete signal, right? Yeah, I did the sampling. Now, if I want to go back from the sample signal to the original and get the frequency content of that, can I do it? In this case, yes, I can. How? You say, well, I only would look at what? I only would look at basically all you have between, let's say, omega s over 2 and negative omega s over 2. If I look at this range, if I apply a filter to all of this and only keep this range, which is 1 omega s, whatever is in that region, that is the original signal. And you absolutely see that in this range, what you have is your original signal. So all you need to do is to apply a filter, right? A filter in the frequency domain, which only has a magnitude of 1 in this region, and anywhere else the magnitude of it is what? 0. So here is 0, here is 1, here is 0, right? We call it the bandpass filter. Or if you only look at one side, you might call it the low pass filter. So exactly by filtering this and keeping the mid region between these two numbers, you are going to get the original frequency plot back. But what about here? Can you go back in this case from the sampled signal to the, or discrete time to the continuous? The answer is no. Why? Because this original profiles that you had, this one and this one, is now replaced by this. If now I go ahead and limit this between negative s over 2 to positive s over 2, what are you going to get? So you're going to get the signal from here and here. So the signal that you will get is this. If I highlight it for you, look, it is going to be like that. As opposed to a perfect rectangle, it is going to look like this now. Okay, above, instead of going like that, now it is going to go like this, so you would never get the original signal back. And this is called aliasing. Okay, this overlap of replicates is aliasing. When does that happen? When your sampling frequency is not bigger than or is less than 2 times maximum frequency in the signal. Okay, yeah? So you can clearly see that. In frequency domain, this is what happens. Now, you might say, fine, you get the replicate, you cannot get it back, and so on. Is there any kind of visual effect or anything? Is there any distortion in the actual signal? What happens if this signal here, if this digital signal is an image or it's an audio or anything like that? If you listen to it, because anything we listen these days is not an analog recording, it's a digital one. So if you look at the digital signal that has aliasing in it or a digital image, what would you see? What kind of distortion because of this overlap you would see? So let's talk about that. So if you look at a simple 1D signal, what's going to happen here? The thing that is going to happen is some of your high frequencies will show themselves as low frequencies. So the signal is high frequency, but you're going to see that as low frequency. For instance, some high-pitched voice that was in the original recording, now you might hear it as a low pitch, right? Correct? So like the voice of a little girl might be heard as the voice of a big old man or something like that. Big, basically low pitch, anything like that. So that can easily happen. As a numerical example, let's say that your signal, original signal, xc of t, is, for instance, a harmonic, and the frequency it has is maximum 9 hertz, or it only has a single 9 hertz frequency in it. Now, when you basically sample this 9 hertz signal, you are going to sample it at only 10 hertz. You know, at least you have to sample it by how much? By 2 times 9. If you at least sample it by 2 times 9, then these triangles are going to be just adjacent to each other, and you can still recover it. But anything less than that, you get the overlap. By the way, this minimum sample rate that you can sample a signal without aliasing and without overlapping, there is a name to it, and it's called the Nyquist rate. Okay, so the Nyquist rate is 2 times what? Omega maximum in the signal. So it says that basically the minimum omega s that you can sample a signal with is equal to how much? Is equal to the Nyquist rate, which is 2 times maximum frequency in the analog signal. Okay, so it's like 2 times omega max, which, as I said, this right hand side is called Nyquist rate. And by the way, this one here, this theorem that says this is your minimum sample time, this guy also has a name. This is called the Shannon-Nyquist theorem, or some people call it Nyquist-Shannon theorem. Okay, which explains the minimum sample time that you need for avoiding aliasing and overlap and proper recovery of the original signal. Okay, so now going back to what we were talking. So this harmonic has a frequency of 9 max, or just 9, and you are going to sample it at 10 hertz instead of at least 18. What's going to happen? Well, this frequency of 9, you're not going to see it as 9. You're actually going to see it as 9 minus 10. So if you look, the alias frequencies, the frequencies that you will see are going to be the absolute value of f, which is whatever the frequency was, in this case 9, minus k. This k is an integer number, so it could be 0, 1, 2, and so on. And this is your sampling frequency. So this is done with a k of 1. So 9 minus 10 is -1. Absolute value of it is 1 hertz. So although the sine wave has 9 hertz, but when you look at the sampled version of that, you're going to see it as if it was only 1 hertz. If there was 8 hertz frequency in it, you will see it or hear it as if it was only 2 hertz. So you see, high frequencies are showing themselves as what? As low frequencies. So you can understand it better, here I have added this picture from Geek4Geeks. This is a very good website. I really like it. The people who make this website are really knowledgeable in what they are doing. So this picture is really interesting, and you can see that. And I can give you a MATLAB code to reproduce this, but you can see that the actual signal is this one in blue. And I'm not sampling it fast enough, so I only sample it at this sample time. So I get these values here, these red ones. Now, if I only give you these red ones and say pass a harmonic through these red points, what kind of harmonic would you pass through them? If I say do a curve fitting, right? Do a curve fitting, a harmonic curve fitting through these red points and pass a harmonic to them, you most probably will pass this green one. Say, hey, I think this is the signal. And now look at this. What do you see? You see that? This XC has way higher frequency than the sampled version, or the one that you think you can pass through it. So high frequencies appear as what? Appear as low frequencies. And that is exactly what? That is exactly the aliasing. Now, if I did it very fast, so I use the smaller sample point, then what? Then you will get a lot of points. So probably you will get all of this. Right? Let's say stuff like this. Now, if I have all of these new red points, now what? Can you still pass that low frequency yellow curve through them? No. Now you have so many points that if you have to pass something, it has to be what? It has to be basically something like the original signal with a lot of what? With a basically with a big frequency. You have to do it this way. So you can exactly see that 9 hertz or 10 hertz as 9, not like 1, as I explained for you here. Okay, so this is the effect that you can see in aliasing. So what about images? If you have 2D signals, what would happen? Well, some very interesting things. So because, again, high frequencies will show themselves as low frequencies, you are going to see some interesting artifacts. Like what? One of them is called the Moir patterns. Hopefully I pronounced the name correctly. I don't think it should be called Moir or something. It's probably a French name. So if I mispronounce it, I do apologize to that person. But basically what you see here are these edges that are kind of jagged. Really? Yes. Look here. This is like a chess pattern, right? Like a chess black and white. And when you go this way, what are you doing when you go this way? You're downsampling the signal, and downsampling always is similar, gives you the repeated pattern. So I want you to look into this region, or here, and look what you see. You see? Clearly, it's not straight edges like these anymore. Look at what you see here. Look. You see these zigzag jagged edges? Okay, so that is one of the things you can see. Another thing that is interesting you can see are false textures. Look at this image. This is an image, the original image, or at least the image with an anti-aliasing filter. So this is a castle. And now look at this guy here. This is an alias version of it. And you see that you get all of these patterns here on this wall that do not actually exist. Okay? This is happening because of aliasing. So if you see some kind of weird patterns in your images, jagged edges, some textures that should not ideally be there or something, one good reason could be aliasing. You have to look at your frequency content of the original signal. You have to find this omega max and then check whether this condition is this one, whether this condition is there or not. If this condition is there, then you're good. If no, you have a case like this. Now what would you do? Let's say you cannot sample any faster than this. Your hardware that you have, that you use for we call it A to D, analog to digital, basically hardware, the one that takes the sampling, this is all you have. And this guy, the best it can give me for this sampling frequency is, let's say, 100. But my original signal, F max, is, let's say, 60 hertz. Well, because it's 60, I need at least 2 times that, which is 120, but my hardware can only give me 100. If I use it, I'm gonna get aliasing, and the 60 hertz will look like 100 minus 60 would look like a 40 hertz. And I don't want that. So one way that you can handle it if you cannot change the omega S is to change the omega N. And that is the base of anti-aliasing filter with a low-pass filter. So what would you do? You trim your signal before sampling it. How would you trim the frequency content of the signal? Use a low-pass filter. And when I say low-pass here, I'm talking about the right side only. So you basically multiply this by a filter that is only 1 for so much, and then after that it jumps to 0. But this wall here is before this signal ends. So if this is your omega max, this filter here is clearly the cutoff, we call it the cutoff frequency. The omega cutoff of this is clearly less than omega max. You cut it below that, so you get a chopped version of this like that. Now, if you take a sample of that with omega S or FS and get replicate of that, these replicates will not overlap. The question is, what cutoff frequency should I pick so these guys won't overlap? Well, it has to be less than or equal what? Omega S over 2. So if this one is less than or equal omega S over 2, or in the hertz, this is F cutoff, is less than or equal Fs over 2, then you are good, correct? Because you exactly chop it at half of that. And so, you know, when you sample it, these guys are going to be repeated at distances of omega S. Since this guy is omega S over 2 and this one is omega S over 2 or smaller than that, then there will be what? No overlap. So this is what we call an anti-aliasing filter that you see it in so many places, including some PID controllers. if you see a PID controller with a filter, which we call PIDF, if you look at the filter part of it in MATLAB, it says, do you want to use anti-aliasing? So that's the meaning of it. Cut the high frequencies to no more than omega s over 2, and then sampling it. Now, is there any drawback? Is there any trade-off? Sure. When you are removing some of the high frequencies in an image, you are going to blur it. If it's a audio, you are going to remove some of the high-pitched voices or some of the sharpness in a signal or anything. Okay, so you lose a little bit quality in that signal or high pitch in the voice or something, but at least you are not going to get these weird artifacts or something that do not exist. Okay, so this is the essence of aliasing and Shannon-Nyquist theorem and anti-aliasing filter. So hopefully the video was useful to you. I'll see you in the next lecture. Thank you.